today we'll be doing reversing and binary exploits. So I'll start with reversing for now. So I'll start with Kalpana CTF's questions. The first challenge was reverse me, and usually you'll be given the binary and something hidden inside. You strings on the binary. You should be able to see anything which will be printed directly as printf and some string and not a variable, and you can see there is the flag there. So it usually goes it's a very basic reversing. Now I'll go ahead and there was another challenge in Kalpana CTF which was a friend. Okay, so we'll go ahead and run the friend, enter random thing. It's loading. Okay, so this binary asks for a secret, and if you enter the secret it tells you if it's a wrong password or correct password. It's usually here where you get obfuscated thinking you might have to guess the password, but you can go ahead and exploit the binary. So we'll start with strings. And from this you can see the directly printed things, but there is not any flag here. So first thing we'll start with is GDB. It's a debugging tool. It's also used for disassembling binaries. So we'll start with GDB and you enter your binary name. It should be pre-installed. Is everyone with me right now? GDB should be on your Ubuntu too. You'll see GDB and not Peda. I'll get to that point later. So first thing you do is do info functions. You'll see what are all functions there, and you have usually these are all the functions which you call, or the inbuilt functions every time you write a program on C. So this is the main function, and this is another function which is not one of the standard functions. We can start disassembling by typing dis as main, or you can complete the whole thing. So if you know x86 instructions, you can go ahead and read it directly, but usually many people don't know how the instructions work. So usually you might have studied from the MPCA. If CS students are right now here, the move you are familiar with move, and yeah, that's all I think. So x86 instructions are totally different, and they have different kinds of registers. So we find nothing useful in main, and none of the place I find secret function called. So we can go ahead and disassemble secret now. So I find a bunch of numbers here. So is any of you with me right now doing this? Oh wait, you don't have the binary. I'm sorry about that. I'll give you the binary. And as a short exercise, you can start taking all those numbers and decode it and find something meaningful, just the last numbers. Extract them by chaining commands, different commands, grep, awk, which you were taught in the Linux classes, and extract all these numbers and try to get something useful. You can do it right now, or you can do it later. So this is very basic reversing using GDB. And yeah, is there anything you want to ask till now about reversing?
Yeah, so the reversing that you're showing us now is similar to what we are kind of learning in our MPCA,
ARM.
but this is
Yeah,
86 and that is ARM That's the difference, right?
yeah, that's the difference. X86 have a lot more instructions compared to ARM, because ARM tries to keep the power usage minimum, while x86 needs more performance compared to the power usage.
So what are we like exactly finding using reversing? I mean, I didn't get that. What sort of a flag would we be
Uh,
looking?
yeah, so in the first reversing, uh, you saw the flag, right? It was like flag reverse engineering.
Yeah.
Yeah, so that's how it's usually put in CTFs. So how these there are forensic scientists, right? And people start when people hack, they put in some ransomware or malware which is compiled. Now you can't get the source code for the compiled program or the virus, because your hacker wouldn't just give it to you. So what they do is they take these binaries .exe files and they reverse it, and they check what instructions are being passed in the registers, and in detail work out how the system is being exploited.
So we can directly get these instructions from the exe files. I mean, which have been used to getting it
These
from the
binary
source code.
files, yeah.
Okay.
Source code might be easier to read, um but if you know good enough, if you know x86 instruction set, you can go ahead and decode everything which is there. But also there are tools like Hopper and Gedra. Gedra is by NSA. They have provided a very good a tool. I'll show it to you right now. Yeah, I forgot about that. Uh, Sorry about that. It's open source, you can download it. Yeah, so it's by NSA. You can download Getra. It's just a zip file. You can extract it, and once you've done extracting, you can make this executable and /Gedra run. So what Gedra does is it'll take the binary, it'll analyze all the instructions and give you a text as close as possible to the source code. So it's very useful while you're reversing. So there was a recently a PESU CTF. Let me start with that. There was a binary called return, and I have it loaded here. You can create a new project and import files into it. So if you see file, import file, you can add any file. And since I'm using the binary return, I'll just double click on it. And it'll ask me that thing is not been analyzed, would you like to analyze now? Just click on yes, analyze. So we give it a little time to analyze. I think it's done already. This binary is not written in C, it's written in Golang. So if you put it in GDB, you won't find the standard C libraries imported and all that. So if I could show it right now. Printf, I think, yeah, this is C. It is written in C. Yeah, one of them is in Golang, the main one. Okay. So when you use GDB on Go files, you're not able to clearly understand what's going on, because C codes are really optimized on hardware level and the instructions are easier to read. Yeah, so this is the Golang. There are many functions there, and it's not similar to what you saw in C when you disassemble a C. So at this times you can use Gedra. It's really useful. It will reverse any binary you give. And here is main function. So you can see it will give you a code as close possible to the source code. If I run that once, /return, and it's expecting an input. No, it's asking for an input. So the input you enter should have the first letter as C, A, N, D, Y underscore is nice. And once it's done, it's going through while loop and doing something. It's modifying the buffer, the storage space. Is anyone having trouble understanding till this point? If I'm not clear enough, I can repeat. Should I go ahead?
Yeah, go ahead.
Okay, so candy is nice. That's not the end of it. So it's going through each letter. One U here is unsigned integer 1. When you AND any 32-bit number, this character is being converted to a number and being ANDed with one unsigned integer, which means that the least significant bit, it's if you AND with another number, if it returns 1, it is an odd number. If it returns 0, you know it is even number. So if it is even number, it gets into the condition, and if it's not A to Z, it keeps the underscore as it is. If it's an odd number, it is changing its case. Odd number here being ASCII value of that particular letter. Once that's done, it's calling function 2. So here we can go ahead and click on function 2. Function 2 is what it's basically doing is it's just hashing the input. So this input candy is nice with even ASCII letters being capitalized. -x20 is -32. The space between small letter and the large letter ASCII value is 32. So if you just subtract it, you get back the capital letters. So this edited text is being passed to the function 2. Function 2 is just giving out the hash. So that was the flag, the hashed text. So this was basic demonstration of how reversing is done.
So can most challenges be solved with tools like Gedra and stuff, or should we learn the x86
No, you don't have to
architecture?
go learn x86 instructions. It's fine if you use Gedra. There is one more called Hopper. I don't think I have it installed right now. Yeah, I don't have it installed. Hopper is another tool. If you're on Windows, there is IDA Pro. Has anyone used it?
Yeah, I've used IDA Pro.
Yeah, that is a little more bit detailed. I'll show you how. So I'll analyze this another binary called comparinator. I think it's done analyzing. Yeah. So there are a lot of nested ifs. This is actually the flag. If you load this into IDA, instead of these hex values, you will directly get the letter. So it's a bit easier there, and you get a graph format. If there are any if conditions, you'll have like a data flow diagram. It's a lot better than looking at hex values. It's your choice. There are many tools. You can use one of them.
One small doubt: are these, the reversed programs only for C and Go, or are they for
Any
C++, Python, and stuff like that?
Python is interpreted language, so when you see Python, it's just direct. It's not compiled. So you do get. Yeah, I remember in one of the CTFs, they give you a pyc.pyc. It's a object file from Python. Yeah, thanks. You reminded that there is a tool for reversing .pyc files. It's supposed to be uncompiled 2. There was supposed to be another one. Yeah, uncompiled 6. So it's one of the good. It's a pip package. You can just directly install it. Directly install it. There are instructions there. Uncompiled 6. What it does is it takes the object file and gives you back the source code directly. So in one of the CTFs, it was that the Python code read a file from the server, encrypted it, and displayed it to you. So they give you the .pyc file. You have to analyze how it's encrypting. Is it doing base 64 and how it's jumbling the words, and you do the total opposite of it to get back the flag. So that was one of the things. Yeah, I think I'm done with reversing for now. Any doubts till now?
No doubts.
Okay, is everyone using Ubuntu or on their Linux systems for now?
Yes, I'm there on Linux.
Everyone else? I'll assume yes. Okay. Okay, cool. You can try it out later, because I'm about to start buffer overflow. You have to pay close attention to what I'll be doing. You might have attended the OS classes and looked at how a program, every time you execute a program, a program stack, like a frame stack, is created in your memory in OS class. So you have a frame created, a program frame, and here is a stack. Here is where all the local variables go. Here is the text, the code. Here is the data. All your global variables go here, and here is heap. So every time a local variable has a integer or a text, characters, everything goes here. So if you create an array with 50 size, it gets filled up from here, from the top. And anytime you use dynamic memory allocation like malloc or calloc, it gets filled from here. From it fills in heap and goes on like this. So this is usually how the program frame is. Now what I'm about to show you is a Stack Overflow. So first vulnerability in this code is that getS is vulnerable to buffer overflows. That's why every time you compile, do gcc buff.c, you'll get a warning that getS is vulnerable, and you should instead use fgetS. Warning, getS function is dangerous and should not be used. This is directly given by the C compiler, so you should avoid using it, even though teachers use it during classes. So yeah, I'll start with that. So first thing you have to do is disable stack protection. By default, stack protection is on, and this is the compile instructions: gcc buff.c -fno stack protect. So once you compile it, the stack protection will be off. We'll go ahead and look at buff.c. So this is a 16 byte character array, and there is an integer pass check equal to 0. It's checking if it's pass, if the entered password is pass. Here we are using getS to get the input, and if it is, yeah, it gives you 0 if the things are equal. So if it's 0, it will go to the else state, and pass check will turn to 1, and if pass check, you're fully authorized. So let's run the a.out file. So it asks me to enter the password, so I entered. So this is the password, so it let me in. So let's enter a wrong password. It says a wrong password. Now if I started overflowing it with more than 16 characters, I think this is more than 16 characters, even though it says it's wrong password, it says fully authorized. This is a C code I got from Secure Programming classes, if anyone have taken that special topic. Okay, so does anyone know why this is happening?
It overrides the value of I don't know what variable is stored in the program, but it overrides it to a chunk value, so it
yeah. So
pass check, yeah.
In the program stack, this has a certain amount of space, and this has a certain amount of space. Once you start filling this, it invades other registers and goes on filling your other memory locations with this junk you entered, and once it goes towards pass check equal to 0, it changes a value other than 0. Here we are checking pass check. If pass check in C, anything other than 0 is true. So as soon as it gets any other value than 0, it gave me full authorization. This is one of very basic buffer overflows. So I'll go on ahead. Yeah, does anyone have doubt about what is happening in the program stack?
Doubts?
Okay, cool. So I'll start with manually how you do a ret to win. So we'll look at the source code. So here is a function which is not called inside the main function. Okay, it is called. So even if it is not called, you can change the return address of this main function to this function and reroute to here using this buffer overflow. So I'll explain in a bit what actually happens. So I'll compile the buff 2.c. with no stack protection, and I'll start disassembling it. So first thing, info functions. I have a main function and function called grant, and info frame. What okay, no stack, sorry about that. I'll create a breakpoint. So when you're using GDB, you can create breakpoints at certain lines. So as the program is going, you can stop the like pause right there in between the program and resume later. So I'll create a breakpoint at the start of the function call, which is the main, and I'll run it. Run, you type run for run. Break, you can either give the function name or the address. So I click on run. You will not usually see this because I have peda installed. Once you run it, it did break at function call main. Now I'll go ahead and check the frame. So these are the registers. Since this is a 64-bit binary, you will see RIP, RSP, RBP. If it's a 32-bit file, you'll usually see EIP, ESP. ESP is extended stack pointer. I'm not sure about what R is. BP is base pointer. I is instruction pointer. So instruction pointer is one which stores the return address. So once it exits main, it directly points to this location. So what we'll do is we'll change this address with the address of grant, so that even without having the password, we can reroute ourselves to get full authorization. So to do that, we'll disassemble main first. So you can check where the getS function is. Here is the getS function, and this is the exact place I'm stopped at. This is a stack pointer, and put as getS. So right before this, I'll create a breakpoint. So break, you put a star and then paste the address. And after accepting it, I want to create another breakpoint to analyze my registers. So I'll stop right after it. So break, so I've created 2 breakpoints. So when you type C is for continuing, like once you stop here you can continue, or if you type run, it will start the whole thing over again. So you press C. So I'm at the breakpoint 2. So it says enter password, and I press C again. It is asking for my input. So as a starter, I'll give 4 capital A's, and it accepted my input. And right now I've stopped at this location. This information you'll not be seeing because you guys don't have peda. I'll come to that soon. So you can check disassemble main again. We are at this point. Now all the memory locations are there in your registers, in your memory right now. So what you do is x/20x stack pointer is which stores everything. all the registers, the return address and all that. So I want to check the hex values in the registers, 20 registers from the stack pointer. So RSP. If you're on a 32-bit machine, it should be ESP. Yes, so you can see my input right here. Sorry about that. So A in ASCII value is 65, and if you convert that to hex, it's 41. So you can see my 4 entered A's, 1, 2, 3, 4. So this is how many times I've entered A. So we'll go back and look at our RIP instruction, which is a return address. So yeah, keep a note of this. So I'll copy this and I'll have this here. This is the address I should be replacing. And if you go back the disassembly of main, this is the address of function grant. Now I have to replace BD0A, this with this, and to do that you have to do this in little endian format. First you have to overflow all these till this point and then replace this address with this. So first you have to calculate the offset. Since I started entering A from here, it's in little endian format, so it goes A, so 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So till this point I need to replace it with junk and then start replacing it with this address. It is calculating the offset every time is kind of tedious, so you can go ahead and download PEDA. PEDA is Python exploit disassembly assistance. Exploit development assistance. So you just have to run these 2 commands and 3 for your satisfaction. So you just run these 3 commands and you will have PEDA installed. So once you have PEDA, you can directly calculate the offset instead of counting and looking at the registers every time. So delete all is for removing all the breakpoints. So I'll start with how PEDA is useful here for calculating the offset. First thing, you can create a pattern. For that the command is pattern create. You have to be inside GDB PEDA for the pattern create command to work. I'll create a pattern of 100 characters because we don't know how much there is a distance between the character array and the return address. So pattern create 100 and it will store it in a file called pat.txt. So what we can do is R is for run and the input will be R input pat.txt. So what it does is it will automatically start overflowing this particular program with the pattern created and check where exactly it stops, where exactly it okay, there is a breakpoint. So I'll run with the pattern created and it'll tell where exactly it gave a segmentation fault, and these are all the inputs it tried. And then you can type pattern search, and here it will give you the offset size. RSP, yes, this is the offset size, which is 24. Now we have to overflow the register with 24 bytes of junk, and then start entering our vulnerable our address, the grant address. So if you disassemble main, this is the address. So we can use Python here to compile, to create the input. So I have 24 junk is, and then my address in little endian format. How you write this in little endian format is, you take the last two characters and type 0xb0, and then go to the left, from right to left you take next two characters 51 and then 55. Remember, it's not 0b, it's b0, 51, 55, 55, 55, and you can copy it to payload.txt. Usually when you hit enter right here, you see it's something which is not in ASCII, so it puts a question mark. So this is an address which you have to send in bytes. GDB does that on its own. While you do it manually, you have to type B to create it as bytes and not encoded. Since GDB is doing it for me, I have it in payload.txt. So let's create a breakpoint. So break main. Remember, there's supposed to be 0 breakpoints when you do the pattern search. So I break at the first line and then run it. So I am here, then disassemble main. Yeah, so get s. Sorry about that. So I create a breakpoint here. Oh my god. So I created a breakpoint too, and then right after that now what I'll do is I'll run it from the start, but with the input from our payload.txt. So it put a breakpoint at 1. I continue. It does ask for input, but I've already entered using the payload.txt. I click on continue. I am at breakpoint 3. Now let's check our registers. Take our RSP. So the RIP instruction is now replaced with our grant function, the return pointer, and then so if I click on continue, it should give me the output. Yeah, so it did say wrong password, but since after the end of the program the return pointer was pointing towards the function grant, it let me in and it printed the grant, whatever the statement was inside grant function. So doing this manually, doing this again and again is very tedious. So there is a Python library pip package you can download called pun tools. So it is pip3 install pun tools. This is very useful when you do binary exploit. It makes it way easier to do buffer overflows. I'll show you. In Kalpana CTF there was a pun challenge. Go ahead and so yes, all this while I did it while the program was running. What happens is usually in a system there is a ASLR on. ASLR is it randomizes this memory location every time you run the program, so you have no idea of knowing if it's the same address on a remote machine. To switch that off, you can type this. You have to be a root echo 0. Yeah, this is the file. The usually it stores a number 2, which means the ASLR is on. When you type 0, the ASLR is switched off. So you don't have to worry about having the program running constantly. You can just switch it off and go on developing your exploit and then rerun the program again with the same addresses. That's why you saw the same address for grant function every time I ran the program. So there is one more thing. I did no stack protect. So when I did gcc no stack protect, there is one more thing called no pi. Pi here means position independent executables. Usually what it does is when oh yeah, I have to show you the pun tools. Yeah, so this is pun tools and this is how you usually exploit. It's very short exploit. Once you find the offset, you can directly code it in, and it's very easy to do buffer overflows with pun tools. So here I'm using PIE, that's the binary here. If I don't give this, what happens is when you try to get an address from pun tools, it gives you the address from the addition to the base address, like it's like an offset. The base address is like an offset. If there is no pi, you can directly address it, you can directly call it without any worries. So what this function I mean this source code does is, yeah, so it opens a file. There is a win function. It opens the files and displays it, and that win function actually has the displays the flag. And then it's not called anywhere. You go, the main function calls the vulnerable function. Vulnerable function here has getS and welcome your name. Yeah, before it does that, it gives you an address. It gives you address of this function. This is the direct address of the function and not the offset address. So using your exploit, you extract, you can ignore this for now. You are working on a local machine, so your ELF, your x86 binary is PIE, and the process should be named p equal to elf.process. And when you do p.receive, it starts running the program and stops at the first line. So once you receive the first line, it will decode. Decode is because they are printed in bytes instead of normal UTF encoding. So you split it, and I receive the vulnerable address. So once I receive the vulnerable address, I'm sorry about that, this thing prints the address from the base address, like an offset address, not the direct address. And puntools here extracts the direct address. So once you have these two, you can directly find the base address. Once you have the base address, you add the direct address of win of this function, and then you convert it into a little endian format of 64-bit. You add the junk after finding the offset. Here our offset was 72 characters long, and then you send the payload and receive the answer. That's basically how it works using puntools. It's much more easier than you doing it again and again. Puntools also helps in a remote, if the binary is hosted remotely, you can send the payload to the remote address, like when you netcat into a machine and the program is running there, you can use that. Instead of elf.process, you just type the host, which is the IP address, and the port number where the binary is running or executing. So I'll execute and show the Python exploit. So it's Python 3. And stack, and this is the architecture, 64-bit little endian format. This is the information displayed by the puntools. This is the vulnerable address I received, which is the address of vul. It is using the offset from the base address. So I subtract the actual address and get the base address, and after overflowing, I fill it with the address I need to go, which is the win. I don't need to go to the register and find every time. Puntools does it for me using this function elf.symbols. So once that's done, it will give me the flag, which is this. It read the file, the function read the file and displayed it, even though the function was never called anywhere. So that was for today's class, and this week's assignment will be protostar.